Hello, good morning, good afternoon, or good evening. It's me, Sumit from Nepal Engineering College, and today I am going to present my slide on comparison of one and two-dimensional models in HEC-RAS for the study of floods in Guia Ephemeral River, Cartagena, Spain. First of all, I would like to acknowledge Nepal Engineering College for providing such golden opportunity to do final project at UPCT under Erasmus Plus. Also, I'd like to thank Universidad Politécnica de Cartagena for selecting me in the Erasmus Plus scholarship program at UPCT, and also I would like to give special thanks to Erasmus Plus unit for their financial support. And I would like to express my sincere gratitude to Professor Jose Maria Carrillo Sanjin for his guidance, dedication, and the invaluable support during the completion of the project. Also, I would like to thank David Morrell and our Professor Durga Prasad Bhandari for their support and help during this project. So without any delay, I want to start my presentation. The content of my presentation are divided into 6 topics: introduction, basics of open channel flow and HEC-RAS, case study, results, conclusion and recommendation, and references. Among many natural disasters, floods are very common throughout the world. They are dangerous and can impact a significant area. And so many people's lost their life every year due to the flood. I have tried to discuss about the impacts of the flood. First of all, there is you can see loss of human lives. Second one is damage to the properties. Third one is destruction of the crops due to flood. The crop may destruct. And fourth one is loss of livestock. So many animals and livestock may get lost due to the flood. And here you can see here is scarcity of potable water due to the flood, because when the flood occurs, then the potable water is mixed with flood water and there is scarcity of potable water, and due to which the waterborne diseases may spread. And last one is the deterioration in water quality. These are the major impacts of flood. Now we have to know about the causes of the flood. The main causes of the flood is rapid urbanization. Due to rapid urbanization, the surface gets most of the surface gets impervious, and there will be decrease in the infiltration, because we use bitumen for road construction and concrete for the construction of other different structures. So most of the area is covered by these materials, impervious surface. So due to which the infiltration decreases, and as a result surface runoff increases and the hydrograph will be changed. As a result, flash flood will be frequent. This is the major cause of the flood. Next one is unplanned and uncontrolled development on floodplains and blockage of the drainage path. Due to blockage of the drainage path, the water will be collected and as a result flooding occurs. And also the major cause is climate change. Due to the climate change, the flood will occurs frequently, because due to climate change there is increase in the temperature, and the ice melts, and as a result there is rise in the water level on river as well as on sea, etc. Now, what is the objective of this project? The major objective of this project is to compare one-dimensional and two-dimensional hydraulic models in HEC-RAS and recommend the best one for the study of floods in the Guia Imperial River in Cartagena, Spain. Now let's talk about the limitation of the project. The project does not look into the details of the modeling of hydraulic structure. Here hydraulic structure like dam, levees are not modeled, and the tributaries of the rivers are neglected. We only models the major river, and tributaries are not considered here. Also, the combined 1D and 2D model is not prepared. Okay, well, separate 1D and separate 2D models are prepared, but combined model 1D 2D model is not prepared. And in 2D model flow, pattern are analyzed only for two different mesh size, 20 meter and 50 meter. Other smaller mesh size are not analyzed due to different problems in processing, and the cross section are considered rigids. That means no sediment transport has been considered. The effect of sediment was not considered in the hydraulic modeling. And the blocking and obstruction to the flow due to the trees, mud, vehicles, etc. has not been considered in the modeling. Now we enter in the basics of the open channel flow, because we are modeling the river which is open channel flow, so we must know about the properties of the open channel flow. In open channel flow, the top surface of the water is open to the atmosphere, and but in pipe flow this surface is not open to the atmosphere. It is confined in certain diameter or certain sides. So in open channel flow, the flow is under atmospheric pressure, and the flow is due to the gravity, so it needs the slope to flow from higher level, higher elevation to the lower elevation. On the different basis, open channel flow can be classified into different types. On the basis of time, we can divide the flow into steady flow and unsteady flow. In steady flow, the flow parameters like velocity, depth, water surface elevation, etc. remains constant with respect to the time. But in unsteady flow, the flow vary with respect to the time. Similarly, on the basis of velocity of flow, we divide the flow into uniform flow and non-uniform flow. In uniform flow, the cross section of the flow remains constant throughout the length of the channel, but in non-uniform flow the cross section remains vary, due to which the flow parameter changes with the along the length of the channel. Also, based on the Reynolds number, flow can be divided into laminar flow, transition flow and turbulent flow. In laminar flow, the Reynolds number is less than 500, whereas in turbulent flow, Reynolds number is greater than 2000. In between 500 and 2000 Reynolds number, there will be transition flow. And also, based on the Froude number, we can divide the flow into three types: critical flow, subcritical flow and supercritical flow. In subcritical flow, the Froude number is exactly equal to 1. But in subcritical and supercritical flow, Froude number is less than 1 and greater than 1 respectively. Now we talk about the basics of the open channel flow. Now we talk about basics of HEC-RAS. HEC-RAS means Hydrologic Engineering Center River Analysis System. It is computer-based program, and it models the hydraulics of flow through natural rivers and other channels, and it was developed by US Department of Defense Army Corps of the Engineers, and the release of version 5.0 introduced 2D modeling of flow, as well as version 4.1 was able to model sediments. Before the releasing of version 5.0 of HEC-RAS, the 2D modeling is not possible, because only 1D model was developed in the software, so we can do only 1D model before releasing of this version. And after releasing of 4.1, we are able to model the sediment as well. This is one of the benefit for the designer or modeler. HEC-RAS solves the energy and momentum equation to calculate the water surface profile. Among them, standard step method and Venant equation are used for the calculation of the water surface profile. First of all, we talk about the standard step method. This method is used for a calculation of the flow parameters in steady flow. According to this method, the total energy at section 11, which is Z1, this is depth of bed of the channel from datum line, this is Z1. Similarly, depth of flow flow depth y1, and alpha v1 square by 2g is velocity head, and he is the energy loss when flow occurs from section 22 to 11. So by equivalent the energy, we can calculate the water surface, where z is the bed elevation, y water surface, v velocity of flow, alpha is the velocity coefficient, and he is the energy loss, which we can calculate using this formula. And c is the expansion and contraction coefficient, l is the ridge length, and sf is the frictional slope, which are shown in the figure as well. This is the plan view, and this is the longitudinal or profile view of the river. In Saint Venant equation, we divide this into two parts, for one-dimensional and for two-dimensional flow. For one-dimensional flow, we use this continuity equation and momentum equation, where all the required parameters are defined here. Similarly, for 2D Saint Venant equation, we have this equation for continuity and momentum. We can solving this equation, we can calculate the flow parameter. Now let's talk about the computation procedure. In computation procedure, we have to first of all determine the downstream water surface elevation. In case of subcritical flows, supercritical starts in the upper cross section, and after determining the downstream water surface elevation, we assume the water surface elevation for upstream. Then we solve this equation, and finally we check whether the difference is greater than 0.01 feet or not. After comparing if this is within limit, then we display the final values, otherwise we again repeat the procedure and calculate the flow parameters until the difference is less than 0.001 feet. Now input, process and outputs in HEC-RAS. What we have to, any project or any software solves the problem through input, their process, and finally they gives the output. In inputs, we have aerial maps, digital elevation model, channel cross-section data, land use, hydraulic structure, sediments, water quality, stream flow data, water surface elevation, and discharge. These are the input parameter which we have to give into the software. After this, software solve the use this parameter and solve the energy equation and find the parameters. So this process includes steady flow water surface profile calculation, unsteady flow simulation, movable boundary sediment transport computation, and water quality determination. After this processing, following output can be obtained from the HEC-RAS: discharge, velocity, water surface elevation, flow depth, cross-section and longitudinal profiles, flood animations, flood inundation maps, graphs, and tabular outputs can also be obtained after the processing. These are the input, process, and output in HEC-RAS. Now let's talk about my study area. The major salient features are described here. My study area is located on the western part of the, this is Cartagena city, western part of the Cartagena city. You can see this is the alignment of my river, and this river is a drive river bed, and the outlet of the river is located at this coordinate, and it is 187.195 meter from mean sea level. This is the outlet of the river, and upper catchment is predominantly covered with the vegetation, you can see here as well, and lower catchment, or this is the right side, is heavily urbanized, and the river carries the peak discharge of 469 cumecs for a 500 years return period. Now in one-dimensional HEC-RAS modeling, we have our trained data of 2 meter by 2 meter pixel size, land cover data. Most of the study area is covered with terrain, forested wetland, and barren land, and palustrine forested wetland, and the maximum flood for 10, 100, and 500 years return period are 127, 312, and 469 cumecs respectively. While modeling, we give the inflow boundary condition as flow hydrograph and outflow boundary condition as normal depth in terms of the slope. and in cross section of the cross section of the river are drawn at 100-meter intervals, which will be shown in the next slide. And this you can see here, this is the land cover data and Manning's rugosity coefficient. This is the land type and this column represents the Manning's rugosity coefficient. You can see here this area is matched with index number 16. So index number 16 is estuarine forested wetland whose Manning's value is 0.08. From here you can tally. Also this portion is matched with index or ID number 1. So ID number 1 is unclassified, or ID number is also similar to ID number 13 as well, and 13 and 2 as well. So it 2 is developed and high intensity. This is a developed area where human settlement was occurred. So in this way we can find the Manning's rugosity and its land type through the land cover data. And these three hydrographs shows the flow and their duration for different return period: 10 years, 100 years and 500 years return period. This value shows the peak discharge, which is 469 cumex for 500. Similarly, this is for 100 years and this is for 10 years return period. This figure shows the one-dimensional model in RAS-Mapper. We can see this blue line is the center line of the river, and this two red lines show the bank lines, and this last on this line show the flow lines, and this green color show the cross section of the rivers. And this is our terrain data, which is of 2 meter by 2 meter pixel size. Now this is the 2D HEC-RAS model, where terrain data and flow data like hydrograph and terrain size of 2 meter by 2 meter, Manning's coefficient, all are similar to one-dimensional model. And for flow computation, 20 meter by 20 meter mesh size is taken, and we divide this whole flow area into large number of pixels. The total number of cells are 5080 in that flow area, and we give the inflow and outflow boundary condition. After this we run the model and result was analyzed. Now let's watch the results in different terms, like in terms of depth, in terms of velocity, and in terms of flood inundation. Before comparison of 1D and 2D model, first of all we analyze the steady versus unsteady flow analysis in 1D model. In one-dimensional model, for 500 years return period flood, I tried to plot the profile. Here you can see this upper one line is for steady flow, and this lower one is for unsteady flow, and this is the bed level. So due to some error in the inflow boundary condition, here is some sudden rise in the elevation of the water, and we can see that the water surface elevation in unsteady flow is lower than that of steady flow. Similarly, this is profile, and this is the cross section of the river, where steady flow line elevation is higher than the unsteady flow elevation. This is for 500 years return period flood. This shows the flow depth for 500 years return period in steady, in unsteady flow. In unsteady flow, the water flow depth is seen larger here, and these also shows the flood inundation as well. And here we can see that this flood inundation area will be maximum in unsteady flow. Also, we are going to compare two different 2D model in which different mesh size are used. In left on, the 50 meter by 50 meter mesh size model is shown, and in right 20 meter by 20 meter mesh size model is shown. This is for 10 years return period flood. In 50 meter by 50 meter mesh size, the analysis is less accurate, and you can see here is this area is also inundated, but here this area is not inundated because this due to less mesh size the flow analysis becomes more accurate. So you can see the you can compare the different mesh size models, two-dimensional models here. Now I am going to compare the 1D and 2D hydraulic model in terms of depth of flow. For this, I divide the whole length of the river into 4 equal parts, and at first, second and third portion, I am trying to calculate the depth of flow from the RAS-Mapper. And similarly, in both 1D and 2D model, the depth of flow are calculated at the same sections, and depth was compared. This is for 10 years return period flood. And first you can see here at this portion the depth of flow is 0.68 meter, but here 1.53 meter. Similarly here 0.23 meter, here 2.24 meter. Similarly 1.39 meter, 2.18 meter. So we can see that in 1D model the velocity the depth of flow will be less than 2D model. Also, for the comparison of depth of flow for 100 years return period, we can see the depth of flow at different sections, and from these two figures we can clearly say that the depth of flow in one-dimensional model for 100 years return period is also smaller than these 2D models. Also for 500 years return period, the depth of flow are compared, and due to some problems in inflow boundary condition, the depth of flow at inflow of the 1D model is seen larger due to some error. Now after comparison of depth, I am going to compare the velocity of flow in 1D and 2D hydraulic models. Like depth, the velocity of the flow may vary at the different sections. In one-dimensional model, at this section 0.45 meter per second, but here 1.45 meter per second. This is greater. Also in 1D model here 4.46, but in 2D model only 1.84. Here the velocity of the flow is higher. Also here the velocity of flow is again less than the 2D model. Comparatively at 2 end the velocity of the flow is greater in 2D model, but at the mid the velocity of the flow in 1D model is less. Similarly for 100 years return period and 500 years return period, we can compare the flow velocity, and we can see there for 500 years return period the 1D model shows higher velocity in all section of the river than 2D model, because in 1D model for high discharge the 1D modeling is not effective, so we have to do 2D hydraulic model. So these value are higher because of their inaccuracy for higher discharge. Now we are going to compare the flood inundation area in 1D and 2D hydraulic model for different return period. For 10 years return period, we can see here in 1D model this area, in this area the inundation area or this flood cover area is very less, but here you can see it will be large. And also here here is some gap between the flow, but here the flood covers the area, and we can see 2D models shows the large inundation area than 1D model for 10 years return period. Similarly for 100 years return period also, this area is not covered by flood in one-dimensional model, but this area is covered by flood in two-dimensional model. Also here is the very less amount of flooding, but here large flood can be seen in 100 years. Similarly for 500 years return period, we can also compare the flood inundation area in 1D and 2D model. Now you can see how the flow occurs in the river in 2D model for 500 years return period. You can see the flow animation. Here the flow increases and again try to decrease. This is the how flow occurs in the two-dimensional model. Now you can also watch the flow animation in the cross section of the river. This is 1D model cross section for 10 years return period plot, how flow will increase in the river and again back to the original level. Now I arrived at the conclusion and recommendation. In non-prismatic river like natural river where the river width is large and bed level variation is non-uniform, two-dimensional analysis is necessary to study the actual flow behavior. Also, 1D analysis can provide a fair result for small discharge, but we already saw for high discharge like 500 years return period flood, the flow velocity flow depth provided by the one-dimensional model is high because in one-dimensional model the analysis is not providing the fair results. For economic and safe design of the dam and other hydraulic structures where the floodplain is very large, actual level of surface water must be known, and from these results it can be concluded that two-dimensional analysis is necessary for natural streams. Also, the research can also be done considering the combined 1D and 2D model for steady and unsteady flow. Here we do to separate one-dimensional and two-dimensional model, but we do not perform the combined 1D and 2D model simulation. So in future, like taking this project, we can use this project for combined 1D and 2D model and compare the results. Okay, thank you.